Some scenes feel like arrivals, and others feel like aftermaths, evidence still moving after the main act is over. Nebulae are neither of those, really. They don't belong to a single moment. They aren't one launch, one photograph, one triumphant flag planted in a bright place. A nebula is a working environment, matter in motion, light doing what light always does, energy moving from one ledger to another. It is gas losing heat and gaining heat, dust grains catching photons and letting them go again, shock fronts turning speed into temperature, radiation carving out cavities, gravity trying patiently to gather what it can. And through it all, a quiet, relentless accounting, momentum, pressure, density, time. It's defined as much by restraint as by spectacle. You don't treat a nebula like a static painting. You don't stop the flow and ask it to hold still for you. Instead, you accept that it is a process, and you learn to read the process through the evidence it leaves behind. Thin shells, bright rims, faint halos, knots and arcs, the particular colours of atoms struck into glowing. Tonight, we'll follow that evidence gently, one calm detail at a time. Back in my office, the air is threaded with a quiet current of sound. A desk lamp warms a folder labelled Nebulae, though somewhere out there a search bar is also typing nebulas, and I don't mind that at all. The kind of label that doesn't promise a single story, only steady work that has to continue. Outside the window is a dark slice of sky. Inside the room, everything feels like a small model of what we're about to study. Air, dust, temperature, light, and time all carefully managed. The lamp is a star of sorts, in miniature, not because it's hot or massive or complicated, but because it emits a stream of photons, and those photons don't care what I believe. They travel, they scatter, they're absorbed, they warm surfaces, they lift tiny dust motes into visibility when the air shifts. The room has its own winds too, soft currents from the heater, a small draft that slips in around the window frame, the lazy movement of air that makes paper edges tremble. A nebula is like that, on a scale large enough to calm the mind just by imagining it. It's a place where flow matters, where a gentle push here becomes a slow wave there. I pull the folder closer. The paper inside is clean and unhurried, the kind of file you can take your time with. My name is Madeline Rowe, and this is the science of nebulae for sleep. We'll begin with a simple promise. A nebula is not one thing. It's a word we use for many related scenes that share a common ingredient, which is matter spread thinly enough for light to travel through it, and for us to see layers within layers. Some nebulae are nurseries, where young stars are being born in clouds of hydrogen and dust. Some are dark lanes, silhouettes against brighter backgrounds. Some are reflections, dust acting like a distant fog bank, glowing only because starlight is falling onto it. And some nebulae are the last visible work of a star's life. Envelopes shed, shells ionized, debris expanding, shock heated, mixed, and dispersed. Tonight's case file focuses on that last set, the nebulae that arrive at the end of a star's long day. We'll move in 3 broad steps. First, a quiet transition, a star like the sun, late in life, shedding its outer layers in episodes that leave delicate arcs, evidence you can read like tree rings, only made of gas and dust. Second, the bright phase that follows, the planetary nebula, which is not planetary at all, but a glowing shell shaped by winds and by geometry, sometimes a ring only because we are looking down the axis of something larger. And third, the violent kind of nebula, the supernova remnant, where the physics is written not in gentle ionization, but in shocks and high temperatures, and the moving edge of an explosion you can measure across years. 3 kinds of evidence: reflected starlight, ionized emission, and shock-heated X-rays. I lift the first page in the folder. A note in the margin reads, "Start with what you can actually observe." That's always good advice, because a nebula is thin. It's not like weather on Earth, where air has enough density to behave as a fluid you can feel on your skin. Nebula gas can be so sparse that the best way to describe it is to say, the atoms are lonely. They're far apart. They go a long time between collisions, and yet that thinness is exactly why a nebula is readable. Light can pass through it. We can see into it. We can watch the way different wavelengths behave, how dust blocks some colours and glows in others, how particular atoms shine at particular energies, how hot, shocked gas radiates in X-rays when it has been heated to millions of degrees. We can't hold a nebula in our hands, so we do the next best thing. We learn to read it. In the office, the lamp makes a pale cone across the desk. Dust motes drift through it, and each one flickers as it turns, bright when it catches the light, invisible when it doesn't. That is scattering in its simplest, friendliest form. Light arriving, light changing direction, light telling you there is something there, even if that something is too small to see directly. Some nebulae are made visible by exactly that mechanism. Reflection nebulae are, in a sense, cosmic dust motes on a grand scale. They glow not because the gas itself is hot enough to emit strongly, but because starlight is being scattered into our line of sight. And that brings us to our first scene. A rapidly dying star. A shell of dust thick enough to hide it. And a nebula that, for a time, shines mostly by borrowed light. The Egg Nebula. I let the name rest for a moment. It's a gentle name, almost domestic. A reminder that astronomical objects often live in the space between science and human perception, between what is and what we call it to make it easier to remember. The Egg Nebula is a pre-planetary nebula, sometimes also called a protoplanetary nebula. That phrase can be confusing, so we'll be careful with it. It does not mean the nebula is forming planets. It means we are catching a star in the transitional interval between 2 phases. Before the star's ejected envelope becomes a bright, ionized planetary nebula, there is a quieter stage where the envelope has been shed, but the central star is not yet hot enough to flood the gas with ultraviolet light. In that interval, there are often few strong emission lines. The gas is not glowing the way a fully ionized nebula glows. Instead, the nebula is illuminated by scattered starlight. It can be faint. It can be compact. It can masquerade as an ordinary star until you look closely, with enough resolution and enough patience. And when you do look closely, especially with a telescope above the blurring of Earth's atmosphere, you can find structure that feels almost impossibly delicate. In the Egg Nebula, one of the most striking clues is a system of arcs, concentric features like ripples or like nested shells. Those arcs are not decorative. They are history. They suggest episodic mass loss, the star shedding material in pulses or cycles, leaving behind a record in the spacing of those shells. On the page in front of me, I note the kind of timescales implied by measured arcs in similar objects. Hundreds of years between arcs in some cases, a cadence that is slow on a human scale and quick on a stellar one. Imagine that, very gently. A star exhaling, not once, but many times. A long, slow breathing out of matter, an envelope leaving in stages. And because the envelope contains dust, tiny grains condensed from material forged inside the star and from chemistry in the cool outflow, that dust can obscure the central source from direct view. So the light we see is light that has escaped through cavities, bounced off dust, and reached us by an indirect route. In the office, I tilt the lampshade a fraction, and the bright patch on the desk shifts. A new set of dust motes lights up. Others vanish. That is the simplest version of what these nebulae do with light. If there is a cavity, an opening carved by an outflow, then light can stream through it like a beam through a crack in a door. If there is dust in the surrounding shell, that beam can scatter and become visible. A pre-planetary nebula can look like searchlights in a fog. But this is not fog. Fog is water droplets at sea level, thick enough to swallow car headlights. Nebula dust is spread across space so vast that it can take thousands of years for the shell to grow and thin. And yet, because stars are bright and because dust is efficient at scattering, we can still see the geometry. This is the first lesson of the file. A nebula is not only matter, it is also illumination. No light, no scene. And the kind of light matters. In a reflection nebula, you are seeing a conversation between photons and dust grains. In an emission nebula, you are seeing a conversation between photons and atoms. Photons ionizing gas, atoms recombining and emitting their characteristic lines. In a supernova remnant, you are seeing a conversation between motion and temperature, fast material slamming into slower material, shocks heating plasma, and hot electrons radiating at high energies. For now, we stay with the quiet transition. A star like the Sun spends most of its life in a stable pattern. Hydrogen fusion in the core, a steady balance between gravity pulling in and pressure pushing out. But stability is not forever. Eventually, the hydrogen in the core is depleted. The balance shifts. The core contracts and heats. Fusion moves into shells. The star expands. In later stages, stars of modest mass become red giants, then asymptotic giant branch stars, A, G, B stars. This is the part of the story where the star becomes, in a sense, extravagant. Its outer layers expand. Its interior becomes layered. There are shells where hydrogen burns, shells where helium burns. There is convection. Big, slow motions carrying material and heat. And the star begins to lose mass at a high rate through a wind. Not a wind like Earth's, a stellar wind, particles flowing outward, carrying away mass and angular momentum. Over long spans, hundreds of thousands of years, this mass loss can remove a large fraction of the star's envelope. In some cases, the outflow becomes dusty enough to hide the star's photosphere. The star is still there, still shining, but it is wrapped in its own ejected material. This is where the pre-planetary nebula is born. Not because something new is igniting, but because something is being revealed. The geometry of the outflow, the episodes in the mass loss history, the shaping forces that have already started to act. One more page in the file. A note. Shaping begins early. That's important. It's tempting to imagine that a planetary nebula becomes shaped only when the central star is exposed and begins to blow a fast wind. But observations show that asymmetry and structure can already be present in the pre-planetary phase. By the time the nebula becomes bright in emission, the sculpting work has often begun. Sometimes that shaping is connected to the star's rotation, to magnetic fields, to the way dust forms and couples to gas. And very often, the shaping is connected to companionship, binary stars, partners in orbit, gravitational influences, interactions that can focus an outflow into an equatorial density enhancement or carve bipolar lobes. We won't need to push too hard on any single shaping mechanism tonight. It's enough to hold onto the main idea. The outflow is rarely a perfect sphere. The outflow carries a memory of the star's environment, and we can see that memory in the nebula's shape. Let's make the office metaphor explicit now, because it will help us stay calm as the physics grows richer. My office is a bounded space. Walls, a ceiling, a window, a door that closes. Inside those boundaries, there are flows. Air from vents, heat from the lamp, tiny pressure differences that tug curtains and move dust. If the air were perfectly still, the dust would settle and the room would become visually quiet. But it never is perfectly still. There is always a little motion, and that motion becomes visible only when there is light to reveal it. Now scale that up. A nebula is a bounded region too, not by walls, but by gradients. A boundary can be a shock front, where supersonic flow slows down abruptly. A boundary can be an ionization front, where ultraviolet photons can no longer keep gas ionized beyond a certain distance. A boundary can be the edge of a dense torus, where dust blocks light and channels outflow along the poles. Inside those boundaries, there are flows. Slow winds from the star's late life, faster winds from the exposed hot core, jets in some cases, and the slow expansion of shells that carry the star's outer layers away into the interstellar medium. And just as in the office, those flows become visible in different ways, depending on the kind of light. If you are looking in visible light with a narrow band filter, you are seeing where particular ions are emitting. That can be beautiful and also misleading if you mistake brightness for mass. Where you see light does not always mean where most of the matter is. Some matter is neutral, molecular, dusty, and better traced at infrared or radio wavelengths. So we will keep our detective's caution. We will ask gently, what exactly am I seeing? The file turns a page. Now we arrive at the planetary nebula. The name is historical. Early astronomers looked through small telescopes and saw small, round, fuzzy disks, objects that resembled planets more than stars. So the name stuck. But the object is not a planet, and the process is not planetary. A planetary nebula is in essence a star's shed envelope, lit up by the hot remnant core. Here is the cleanest way to picture it. First, a slow wind. In the AGB phase, the star loses mass through a relatively slow outflow on the order of about 10 kilometers per second, slow for astrophysics, swift compared to any breeze you've ever felt. That wind carries gas and dust outward, forming an extended circumstellar envelope. Second, exposure. As the envelope is depleted, the star's hot core is revealed. The central object becomes much hotter, tens of thousands of Kelvin, sometimes far hotter. Third, a fast wind. The exposed core develops a much faster wind, hundreds to thousands of kilometers per second, fast enough to catch up with the earlier slow wind. Fourth, interaction. The fast wind slams into the slow wind, shocking it, compressing it, sweeping it into a denser shell. The shell expands, often at a typical planetary nebula expansion speed, around a few tens of kilometers per second. Roughly 25 kilometers per second is a common number to hold onto. And fifth, illumination. the hot central star emits ultraviolet photons that ionize the gas in that shell. Ionized gas recombines and emits light at characteristic wavelengths. That is the glow of the planetary nebula. It's a process that connects dynamics and radiation. A planetary nebula is a dynamical system whose evolution is tightly coupled to the evolution of the central star. As the star changes in luminosity and temperature, the ionization changes. As the winds change in speed and mass loss rate, the shell's density and structure change. As time passes, the nebula expands and thins, and eventually it fades into the general interstellar medium. This is not a single ejection. It is not one clean blast. It is a sustained story of mass loss, interaction, compression, and light. In the office, I can make a tiny version of this with nothing more than breath and dust. If I exhale gently across the desk lamp's beam, dust motes swirl and a thin layer of warm air rises and bends the light slightly. It's not dramatic, it's subtle. But it is a reminder that flow plus illumination equals visibility. Now, planetary nebulae are famous for their shapes. Some are round, some are elliptical, many are bipolar, 2 lobes with a waist like an hourglass. Some are multipolar, with more than one pair of lobes, as if the outflow direction changed over time. And the important thing for a calm mind is this. What you see in a single image is a projection. A nebula is 3-dimensional. Your telescope gives you 2 dimensions. The third is implied, inferred, reconstructed. And the way you infer it is by using more than one kind of observation. You use different filters, you use different wavelengths, you use spectroscopy to measure velocities and build kinematic models. You use wide-field imaging to look for faint halos outside the bright core. You use infrared and radio to trace molecules and dust, because optical images may not represent where the neutral mass is. When you do all that, shapes you thought were simple can turn out to be complex. A nebula that looks like a ring can be a bipolar structure viewed close to Polion. A nebula that looks spherical can turn out to be bipolar when you include kinematics. Even within one object, different ions can trace different zones, an onion-like structure, where more highly ionized species are closer to the star and less ionized species are farther out. So tonight, when we look at the Ring Nebula, we will be kind to ourselves. We will not demand that it be only what it appears to be at first glance. We will treat the ring as a clue, not a conclusion. The Ring Nebula, M57, NGC 6720. A familiar exhibit in the Museum of the Sky. On the desk, I slide a photograph into view, an image in my mind, not on paper, an oval ring of light with a darker center, a jewel-like object hanging in Lyra. The instinct is to describe it like a donut, a halo, a smoke ring, and that is not entirely wrong, but it can be incomplete. A bipolar nebula viewed near Polon will be perceived to have a ring structure due to the brightness of the torus. In other words, if a nebula has a dense equatorial ring, or torus, like a belt of material around the waist of the system, and if the bipolar lobes extend out of the plane of that belt, then looking down the axis can emphasize the ring and de-emphasize the lobes. You see the waist. The lobes, extended along the line of sight, become harder to recognize as lobes. Some models suggest the bipolar axis of the Ring Nebula is inclined only about 10 degrees relative to our line of sight. 10 degrees is small. It means we are almost looking down the polar axis. That one geometry can explain why a nebula can look like a ring from here and like a dumbbell from somewhere else. There is a calm comfort in that, because it means that part of the mystery is not hidden in a faraway star's secret motives. It is hidden in perspective, and perspective is something we can account for. In the office, if I hold a mug at arm's length and rotate it, its shape changes. From one angle, it is a circle. From another, it is an oval. From the side, it is a cylinder. The mug has not changed. Only my line of sight has. Nebulae teach this lesson with great patience. Now, the ring nebula is not only geometry, it is structure. There are knots, dense clumps in the inner rim. There are arcs and halos, faint outer structures that you might miss in a shallow image. There are layers of ionization and layers of dust and molecular material that do not all show up in the same way. And this is where our detective work becomes especially soothing, because it asks us to slow down and separate what we know from what we assume. We know the central star is hot. We know it is the remnant core of the progenitor star, on its way to becoming a white dwarf. We know ultraviolet photons from that core ionized surrounding gas. We know ionized gas emits line radiation. We know the nebula shell is expanding. We know the shell's shape is influenced by the density structure of the earlier AGB wind and by the later fast wind. We know the optical brightness pattern depends on where the gas is ionized and excited, and on how much path length we have through emitting material along any given line of sight. And we know, this is the quiet part, that brightness is not always mass. Where the nebula shines can be where conditions are right for emission, not necessarily where the bulk of the matter sits. Some of the matter may be neutral, molecular, dusty, and best traced outside the optical glow. This is why, in modern studies, infrared imaging and spectroscopy are so valuable. Molecular hydrogen emission can trace zones shielded from the harshest ultraviolet radiation, dense clumps where molecules survive because they are protected by their own material. Dust emits thermally in infrared. Different instruments can show different faces of the same object. If you only ever looked at the ring nebula in one filter, you would be looking at one chapter of a longer book. So we'll read more than one chapter. We will take a calm tour across wavelengths, like walking slowly through a dim gallery with different lamps illuminating different textures. First, visible light. In the visible, you often see emission lines from hydrogen and oxygen and nitrogen, depending on the filter. Hydrogen's recombination light can trace the general ionized region. Oxygen's bright forbidden lines can trace zones of particular temperature and ionization. Nitrogen can be strong in low ionization regions. You see rims, shells, filaments. It's gorgeous, but it's only part. Second, infrared. In the infrared, you can see warm dust glow, and you can see molecular hydrogen emission in some cases. Infrared can reveal extended structures beyond what's obvious in optical images. Halos, lobes, faint features that change how you classify the nebula's shape. Infrared is also kinder to dust obscuration. It can peer through where visible light is scattered or absorbed. Third, ultraviolet. Ultraviolet observations can detect signatures of the fast wind from the central star, including P Cygni profiles, spectral features that indicate outflowing material. These are the fingerprints of the fast wind predicted by the interacting stellar winds model. Fourth, X-rays. In X-rays, some planetary nebulae reveal hot bubbles, shocked fast wind material, heated to temperatures high enough to radiate in soft X-rays. This was another prediction of interacting winds, later confirmed by X-ray observatories. And already, just by listing those, you can feel the case file settle into place. The nebula is not one picture. It is a system. It has cool zones and hot zones, ionized zones and neutral zones, fast components and slow components. And each telescope, each wavelength, each technique is a different kind of lamp in our office. We turn them on one at a time. We let them reveal what they reveal. We don't rush. If we take this slow, we can also take it gently, because there is a natural rhythm to the physics. Slow wind, fast wind, compression, ionization, expansion, fading, a cycle of sorts, not a perfect loop, because the star is evolving forward and the mass is leaving, but a sequence you can follow without strain. Now, let's return briefly to the pre-planetary phase, because it holds one of the most restful ideas in the file. That stars can leave timestamps in their outflows. The Egg Nebula's arcs and similar arcs in other pre-planetary nebulae suggest episodes separated by roughly consistent intervals, hundreds of years in some measured cases. What could cause that? There are a few candidates: thermal pulses in the AGB phase, episodes where shell burning becomes unstable and the star's structure adjusts, can produce enhanced mass loss. Binary interactions can modulate outflow. Magnetic or dust formation cycles could play a role. The file does not demand that we pick one cause tonight. It asks only that we notice the evidence. We have shells, we have arcs, they are spaced, they are thin, they are projected into our view, and they remind us that a star's final mass loss history is not always smooth. It can be episodic, which means the nebula is not only a shell, it is a stack of shells sometimes. It is a set of nested layers, each with a slightly different age. And that brings us to a concept I find calming, because it is so concrete. Kinematic age. If you know how fast a shell is expanding, and you know its size, you can estimate how long it has been expanding. Size divided by speed gives a timescale. It's not perfect. Expansion speeds can change, and geometry can complicate what size means. But it gives you a foothold. It lets you translate a photograph into a history. And that is what makes nebulae feel like case files. They are evidence you can date. They are events you can place in sequence. They are physics you can connect to time. In my office, the clock on the wall keeps time in seconds. In a nebula, time is kept in arcs and halos and expansion. Hundreds of years between arcs. Thousands of years for a planetary nebula to expand and fade. Centuries for a supernova remnant to change measurably in X-rays. Each kind of nebula comes with its own sense of time. And when you're trying to fall asleep, it can be comforting to borrow a slower sense of time than your own. Now, a short pause in our story. Not a break, just a soft widening. When we say a star dies, we often mean one of two things. For sun-like stars and intermediate mass stars, the end is not a catastrophic explosion. The star sheds its envelope and leaves behind a white dwarf. The death is a dispersal and a dimming. For more massive stars, the end can be a core collapse supernova, a violent explosion leaving behind a neutron star or a black hole. For a white dwarf in a binary system, the end can be a thermonuclear explosion, type 1a, if conditions are right. So there are multiple routes to a nebula-like aftermath. A planetary nebula is not a supernova remnant. A supernova remnant is not a planetary nebula. They can look similarly wispy in some images, but the physics is different. And this is where we'll shift in the second half of our file, from the slow and luminous to the fast and shock-heated. But before we do, I want to make one more careful note about planetary nebulae, because it is one of the most useful pieces of hard science to keep you from drifting into mythology. Planetary nebulae are not giant clouds of material. They are thin shells. The mass in the ionized nebula is often on the order of a few tenths of a solar mass, commonly quoted around 2/10, though it varies. Much of the mass lost by the star can reside outside the bright ionized shell, in the extended envelope, in dust and molecules, in faint halos. The bright part is the part that is lit and dense enough to shine. Again, brightness is not mass. And if we hold on to that, we can appreciate the images without being fooled by them. Now, in the folder, I find a page titled Interacting Winds in Plain Language. I smile because that's exactly what I want. Plain language, soft voice, hard science. Here is interacting winds in a calm sequence. A slow wind from an AGB star builds an extended envelope. When the envelope is depleted enough, the hot core is exposed and blows a fast wind. The fast wind collides with the slow wind. At the collision, shocks form. Shocks compress material into a shell and can heat some gas to high temperatures. The shell expands. Ultraviolet photons from the hot central star ionize the shell. Ionized gas emits. The shell evolves as the star evolves. That's it. No magic, no special effects, just fluid dynamics and radiation stretched over thousands of years. And because the slow wind is not necessarily spherical, and because companions and rotation can create equatorial density enhancements, the interaction can produce bipolar and multipolar shapes. A dense equatorial region resists expansion, while the poles offer a path of lower resistance. So outflows can become collimated, lobes form, an hourglass emerges, and if we look down the axis, we see a ring. If we look from the side, we see a dumbbell. Orientation matters. Now, there is something else here that I find restful. The nebula is a map of limits. The central star can only ionize a finite amount of gas. Photons are a budget. Each ionization requires a photon. The ionized volume is set by the balance between ionizing photons and recombination in the gas. This is a quiet, steady accounting, almost like the way the office has a fixed amount of light, and the brightness of the scene depends on where that light lands and what it strikes. In a nebula, the ionization front marks where the photon budget runs out. Beyond that front, gas is more neutral. Molecules can survive, dust can be cooler. This is why many nebulae have layered structures, with ionized inner regions and more neutral outer regions. It's also why dense clumps can protect their interiors, creating pockets where molecules persist even within a generally harsh environment. A planetary nebula can be, chemically speaking, a factory in motion. Elements created in the star's interior are ejected. Dust grains form. Organic species can be made and destroyed, reformed and processed. It is not the quiet emptiness you might imagine if you think of space as a vacuum. It is an environment with chemistry and radiation and time. And eventually, those products, gas enriched in heavier elements, dust grains, mix into the interstellar medium. They become part of future star-forming clouds. They become part of new planetary systems. They become, in a long and patient way, part of the material that will one day be alive, curious, and lying awake at night listening to a case file. That's a nice thought, and we don't need to push it. We can let it sit in the room like the low hum. Now, I turn the page to the Ring Nebula again, because it is our bridge between the quiet and the violent. Why? Because it teaches us how to read structure. And reading structure is exactly what we will do in supernova remnants. In a planetary nebula, structure comes from winds and ionization fronts and density contrasts. In a supernova remnant, structure comes from shocks, from instabilities, from clumps in the surrounding medium, from the mixing of ejected layers, from asymmetries in the explosion. Both are readable. Both can be reconstructed from careful observations across wavelengths. Both reward patience. So we will carry our method forward. We will not jump to conclusions based on a single image. We will ask, what is glowing and why? In a planetary nebula, optical emission is often from gas heated and excited by photoionization. In a supernova remnant, X-ray emission is often from shock-heated plasma. The causes differ, the evidence differs, the story differs, but the detective work is the same. Now we step into the violent chapter. I shift in my chair. The folder makes a soft sound. Outside, the window is still a dark slice of sky. Inside, the desk lamp is still warm. And I remind myself, quietly, that the most dramatic events in astronomy can be approached without raising your voice. A supernova remnant is the aftermath of an explosion. But the remnant itself is not the explosion. It is the long unfolding of the explosion's consequences. It is debris expanding into space. It is shock waves moving through gas. It is a shell that grows and cools and fragments and mixes and gradually becomes less distinct from its surroundings. Supernova remnants can last for tens of thousands of years. And within that time span, we can sometimes see change over human timescales, especially in X-rays, where sharp features can move as shocks advance. One of the most satisfying kinds of evidence in all of astronomy is motion you can actually measure. Not inferred motion, not theoretical motion, motion on the sky. Motion you can see by comparing images taken years apart. Chandra, NASA's X-ray observatory, has done this for supernova remnants, taking observations separated by years and showing how structures shift. A time-lapse made not by animation, but by patient observation. That is, in a way, the ultimate case file. Because it's not just a snapshot, it's surveillance footage. Let's begin with Kepler's supernova remnant. Kepler's SNR is the remnant of a supernova observed in 1604, one of the last supernovae seen in our galaxy with the naked eye. It is often associated with a Type 1a explosion, a thermonuclear disruption of a white dwarf in a binary system. The details of progenitors can be complex, and we don't need to litigate every scenario tonight. What matters for our purpose is that Kepler's remnant is an expanding shell of hot gas emitting in X-rays. Chandra observations spanning decades can be assembled into a time-lapse that shows the expansion. And the expansion is not uniform, because the remnant is not expanding into perfectly uniform space. The surrounding medium has structure, density variations, clumps, gradients. Where the remnant hits denser material, the shock slows. Where the remnant moves into thinner material, it can advance faster. So the shell's edge changes shape as it grows. This is the second lesson of our file. Even an explosion is shaped by its environment. In the office, if I open a door quickly, a gust of air moves in a wave. If there is a stack of paper on the desk, the wave hits it, curls around it, and the papers flutter differently than they would in an empty room. The gust's shape is shaped by what it encounters. In space, the shock front is shaped by the density distribution of gas and dust around the star. And we can see that shape. In X-rays, shock-heated gas can glow with a brightness that traces where energy is being dissipated, where the shock is strongest, where the plasma is hottest or densest. If you watch the remnant over years, you can see bright filaments shift outward. You can measure proper motions, you can estimate shock speeds, and again, you have a foothold in time. You are not staring into the past as a frozen tableau. You are watching a system evolve. You are watching time made visible. Now, the word shock can sound harsh, so let's soften it with clarity. A shock front is simply a boundary where conditions change abruptly. Velocity drops, temperature rises, density can jump. In everyday life, you see shocks in the bow wave of a boat, or in the compression wave ahead of a supersonic aircraft. In a supernova remnant, the shock is created by the ejector moving faster than the speed of sound in the surrounding medium. The shock heats the gas to millions of degrees. At those temperatures, atoms are highly ionized, and the gas emits strongly in X-rays. So X-ray telescopes like Chandra are ideal for seeing these hot, shock-heated regions. Kepler's remnant, then, is a moving boundary of hot plasma. And by watching it, we learn about the explosion and about the medium into which it expands. We learn where the surrounding medium is dense. We learn where it is thin. We learn how the remnant's energy is being partitioned. And we learn, quietly, that even cosmic violence becomes methodical over time. The next page in the file is titled Elements and the Stars' Last Arguments. That's a poetic title for a scientific point. It refers to something deeply physical, that in the final stages of a massive star's life, the interior can become turbulent and unstable in ways that mix layers that we might otherwise expect to remain neatly stratified. We see evidence of that in Cassiopeia A. Cassiopeia A, Cas A, is the remnant of a core collapse supernova. In core collapse, a massive star builds up an iron core through successive stages of fusion. Iron is a dead end for fusion energy production. Fusing iron does not release energy the way fusing lighter elements does. So when the core becomes too massive, around the Chandra limit, roughly 1.4 times the mass of the Sun, the pressure support fails. The core collapses. In the collapse, conditions become extreme. A shock forms. Neutrinos are released in enormous numbers. The outer layers can be blasted outward. A supernova happens. Again, that's the dramatic summary. But what we can observe now, centuries later, is the remnant. A shell of expanding debris. Hot plasma. X-ray emission. And crucially, the distribution of elements. Because the layers of the star, where silicon, oxygen, neon, and other elements were produced, are not necessarily arranged in the remnant the way a simple textbook diagram might suggest. In Cassiopeia A, detailed X-ray spectroscopy and imaging can map where particular elements are emitting, and those maps can show surprising patterns. Regions where silicon appears farther out than expected, and neon appears farther in than expected, implying that material from different layers has been mixed. That mixing is evidence of turbulence and internal motions before the explosion, and of complex dynamics during the explosion itself. This is a profound thing, but we can hold it lightly, because we don't have to solve the whole supernova engine tonight. We only need to understand what kind of evidence a remnant provides. A remnant is a forensic scene. Elements are not just chemistry. They are history. They tell you what layers were present, where they ended up, and how violent and asymmetric the explosion and its precursor motions may have been. In the office, if you drop a jar of different coloured beads, the pattern on the floor tells you something about the drop and the bounce. Which direction did it fall? What angle? What obstacles were in the way? In Cassiopeia A, the beads are elements, and the floor is space, and the bounce is the explosion and the surrounding medium. And because we can see different elements in different wavelengths, we can map that pattern. This is where I like to slow down even more, because it's easy to get pulled into excitement here. And excitement is not what we're doing. We're doing calm. So let's take it slowly, as if we are sorting papers into folders. Folder 1, Planetary Nebulae. A star like the Sun sheds an envelope through a slow wind. A hot core appears. A fast wind compresses the slow wind into a shell. Ultraviolet light ionizes the shell. The shell glows in emission lines. The structure is shaped by density distribution, winds, and often binary interactions. The nebula expands at a few tens of kilometers per second. It fades over thousands of years. Folder 2, Pre-planetary Nebulae. The star has begun shedding its envelope. The shell is dusty and can obscure the central star. The central star may not yet be hot enough to ionize the shell strongly, so the nebula is seen mostly by scattered starlight. Structure and shaping can already be present. Arcs can indicate episodic mass loss separated by hundreds of years. Folder 3, Supernova Remnants. A star explodes, either thermonuclear type 1A or core collapse. Ejecta expand at thousands of kilometers per second initially. A shock front forms as the ejecta sweep into surrounding medium. Gas is heated to X-ray emitting temperatures. Remnants evolve over centuries to millennia, and in some cases we can see measurable changes over decades. Element maps reveal mixing and asymmetry. Those are the folders. Now, the trick is to blend them into one story without rushing, because they are connected by a deeper theme. Stars live by balancing forces, and they end by redistributing material. A nebula is a redistribution scene. It is matter leaving one form of order and entering a more diffuse one. And light is what lets us witness the redistribution. So, to keep our story unified, I want to return to the office metaphor one more time and extend it. Picture my office as a nebula, not because it is large, quite the opposite, because it is bounded and because it is full of gradients. There is a warm zone near the lamp. There is cooler air near the window. There is a subtle flow from the vent. There are dust grains that float and settle depending on air currents. And there is a boundary at the window, glass separating inside air from outside air. If I were a tiny sensor floating in this office, my world would be defined by those gradients. If I had a little spectrometer, I could measure the lamp's colour temperature and the way it changes after passing through dust and paper fibres. If I had a little anemometer, I could measure the air currents. If I had a thermometer, I could map the warm and cool pockets. From those measurements, I could infer the structure of my world. That is what we do with nebulae. We are tiny sensors looking in from far away. We can't step inside, so we measure light. We measure spectra. We measure shapes and motions, and we infer. This is why a nebula is such a perfect case file for sleep, because it is both beautiful and methodical. You can drift on the beauty, and you can relax into the method. Now let's take a long, calm walk through the evidence types in a way that feels like strolling down a corridor of labelled rooms. Room 1, Scattered Light. The Egg Nebula and other protoplanetary nebulae can be hard to detect because they do not have strong emission lines. Their illumination is scattered starlight. That means the dust is doing the visible work. Dust grains scatter light, and the scattering can be more efficient at shorter wavelengths, which is one reason some reflection nebulae look bluish. The nebula can show beams where light escapes through cavities. It can show arcs where shells are present. It can show asymmetry that tells you shaping has begun. If you want a single calm image to hold in your mind, hold this: a star at the center, wrapped in dust. Light finding the paths of least resistance. The paths becoming visible like searchlights in a thin mist, and around that, faint concentric arcs, shells laid down over centuries. Room 2, photo-ionized emission. When the central star becomes hot enough, ultraviolet photons ionize surrounding gas. In a simplified picture, the ionized region forms where the photon budget balances recombination. The nebula's gas is mostly hydrogen and helium, with trace heavier elements that can dominate cooling and emission lines. Close to the star, gas can be highly ionized. Farther out, ions are less ionized. This creates onion-like ionization structures. Different filters show different parts of that onion. The nebula's shell expands, often at tens of kilometers per second. The shell's density structure and thickness change over time, coupled to the central star's evolution. The interacting winds model predicts fast winds from the central star, remnants of the AGB envelope around the ionized shell, and hot bubbles detectable in X-rays. All of these have observational support across decades of study. If you want a calm image here, hold this: a hollow shell, thin and glowing. A hot core in the middle. A denser waste where the earlier wind piled up. Lobes where expansion was easier. And a faint halo outside, the remnant of the longer, slower mass loss. Room 3. Shock-heated emission. In supernova remnants, the key illumination mechanism is shock heating. The shock turns bulk motion into thermal energy. Gas temperatures climb to millions of degrees. At those temperatures, X-ray emission becomes strong. Observations separated by years can reveal expansion. Brightness patterns can reveal density variations in the surrounding medium. Element maps can reveal mixing and asymmetry. Kepler's remnant shows measurable expansion across decades of observations. Cassiopeia A shows evidence that the star's interior was not perfectly layered and calm before it died. Turbulence and mixing left signatures in where different elements ended up. If you want a calm image here, hold this: a shell expanding, not uniformly, but with a slightly uneven edge. Filaments moving outward in slow motion, like a high-speed splash played back at a gentle frame rate. Heat as a glow, not as a burn. Time as a visible drift. Now, we've walked through the rooms. Let's sit with each for a bit longer, because sitting is how you turn a tour into rest. I turn back to the Egg Nebula. Pre-planetary nebulae are short-lived in cosmic terms. They are a transition. A star is shedding mass rapidly, but the central star has not yet heated enough to light the gas in emission. So the nebula's visibility depends strongly on geometry, dust content, and illumination. The arcs and shells suggest episodic mass loss, and those episodes can be connected to the messy internal life of an AGB star, shell burning, convection, and instabilities like thermal pulses. Thermal pulses are like deep interior weather. Not surface weather, but shell weather. Fusion turning on and off in layers. Pressure building and relaxing. The star adjusting and losing more material. When those pulses happen over long periods, they can leave nested shells in the circumstellar environment. So when you see arcs, you are seeing the star's last few centuries of breath. That is intimate, in a distant way. And because those arcs are thin shells projected onto the sky, what you see is a cross-section of a three-dimensional structure, another reminder that geometry matters. Now we turn to the planetary nebula phase. This is where the star becomes, briefly, a lantern. The exposed hot core emits ultraviolet photons. The shell glows. For a time, a planetary nebula can be one of the most visually striking objects in the sky through a telescope. But the phase is short. The nebula expands and becomes too diffuse. The central star cools and fades into a white dwarf. The glow diminishes. The material merges into the interstellar medium. The nebula is not a permanent monument. It is a transient display. And its shape is a clue to the dynamics that created it. Round, elliptical, bipolar, these categories exist, but they are limited by the fact that images are two-dimensional, sensitivity dependent, wavelength dependent, and affected by viewing angle. Deeper images reveal faint features. Different ions trace different structures. Optical light may not represent the neutral component. Field of view can hide outer lobes or halos, so classification is provisional. This is a wonderful way to think. If you're trying to relax, provisional thinking is gentle. It says, we know what we know, and we leave room for what we don't yet see. Now we return to the Ring Nebula with that gentle mindset. The Ring Nebula's inner halos may represent projected images of bipolar lobes. Its intrinsic structure may resemble bipolar nebulae, like the Dumbbell Nebula. A 3D model of kinematic data suggests a small inclination of the bipolar axis relative to our line of sight. So the ring is not a contradiction, it's a perspective. The ring is the bright waste. The hole in the centre is not empty space so much as a region, with less emitting path length along our line of sight, and perhaps a lower density or different ionization conditions. The knots along the rim are denser clumps, resisting dispersal, and outside, faint structures can extend the story beyond the bright central ring. In a modern sense, the Ring Nebula is a reminder that objects you think you know can still be deep. Now, we shift back to supernova remnants because they carry the same lesson. A supernova remnant's bright filaments in X-rays and optical are not the whole mass. Some mass may be in cooler components, traced by other wavelengths. The remnant interacts with the surrounding medium, and the medium shapes it. The remnant's appearance depends on energy, density, and time. In Kepler's Remnant, time-lapse shows expansion. In Cassiopeia A, element maps show mixing. In both, careful observation turns an image into a story. Now, a soft module, one of my favourite gentle explanations, because it makes the hard science feel like common sense. Why do different wavelengths show different things? Because matter interacts with light differently depending on the size of structures, the temperature, and the electronic states of atoms and molecules. Dust grains are comparable in size to optical wavelengths, so they scatter optical light efficiently. Warm dust emits in infrared. Cold molecules emit at radio and millimeter wavelengths. Hot plasma emits in X-rays. And atomic transitions occur at specific energies, producing emission lines at specific wavelengths. So when you change wavelength, you change what you are sensitive to. You change which components of the nebula can speak. Optical is often the language of ionized gas. Infrared is often the language of dust and molecules. X-ray is often the language of shocks and hot bubbles. Radio and millimeter can be the language of cold molecular envelopes. And the full story is written across all of them. You wouldn't trust a case file built from only one witness, so we don't trust a nebula story built from only one wavelength. We gather multiple statements, we compare them, we build a consistent picture. And then, if we're wise, we keep that picture flexible enough to improve with better data. Now, let's take a deeper breath and settle into one long, continuous narrative, one that moves from the quiet end of a star like the Sun, through the bright planetary nebula and into the violent remnants of supernovae, while keeping the tone soft and the steps clear. A star is born from a cloud. That part of the story is familiar, but to understand nebulae as end-of-life evidence, we start later. We start with a mature star that has burned hydrogen in its core for billions of years. When core hydrogen is gone, the core contracts and heats. Hydrogen burning moves into a shell. The star expands into a red giant. Later, helium can ignite in the core, then move into shells. The star becomes an AGB star, a luminous, cool giant with a layered interior and a large, extended envelope. In this late stage, the star loses mass at an impressive rate. A slow wind carries material away. Dust forms in the outflow. Molecules can form. The outflow builds a circumstellar envelope. Sometimes the envelope becomes thick enough to obscure the star's surface at optical wavelengths. The star becomes, in a sense, hidden in its own history. Over time, the envelope is depleted. The star's hot core is revealed. The core heats rapidly compared to earlier stages, moving across the Hertzsprung-Russell diagram to higher temperatures at roughly constant luminosity for a time, as the remaining envelope mass becomes very small. When the core is hot enough, ultraviolet photons pour outward. They ionize the surrounding gas. The shell lights up. This is the planetary nebula phase. The interacting stellar winds mechanism helps compress the earlier, more diffuse AGB outflow into a denser shell and accelerate it. The fast wind from the central star can reach velocities of thousands of kilometers per second. The nebula shell expands at tens of kilometers per second. The density structure of the earlier wind, plus any equatorial enhancement, plus any binary interactions, shape the nebula into rings, ellipses, lobes, and sometimes more complex forms. As time passes, the nebula expands and becomes more diffuse. The ionization front evolves as the central star evolves. The nebula's brightness changes. Eventually, the nebula fades. The central star becomes a white dwarf. The ejected material merges into the interstellar medium, enriched with elements and dust grains produced in the star and in the outflow. That is the gentle ending path. But for more massive stars, the ending is not gentle. A massive star continues fusion through heavier elements, building an iron core. When the core becomes too massive, it collapses. A supernova occurs. The outer layers are ejected at high speed. A shock front expands into the surrounding medium. The shock heats gas to X-ray emitting temperatures. The remnant's edge moves outward, and over decades we can sometimes detect changes in that edge. The remnant's internal structure reveals mixing, asymmetry, and interactions. Element maps show where different layers ended up. That is the violent ending path. These paths are different, but they share a theme. They return material to space. They turn a star's interior products into interstellar ingredients, and they create nebulae that we can observe and interpret. Now, I want to slow down and linger on one scientific detail that is quietly beautiful. In both planetary nebulae and supernova remnants, shells and boundaries are central. A boundary is where change is concentrated. In planetary nebulae, the bright shell is where density and ionization conditions produce strong emission. In supernova remnants, the shock front is where heating and compression are strongest. Boundaries are readable. They are, in a sense, the lines of the story, and that makes nebulae feel like diagrams drawn by physics itself. It also makes them soothing to follow, because there is order in the complexity. Even when shapes are intricate, they arise from a few principles applied over time. Flow, compression, radiation, cooling, gravity. If you keep those in your pocket, you can walk through most nebula stories without getting lost. Now, let's take Kepler's Remnant again, and let's treat it like a calm experiment. Suppose you have a sudden release of energy, an explosion. The ejecta move fast. They expand. At first, the ejecta are essentially free expansion because they haven't swept up much mass. But as the remnant grows, it sweeps up more and more interstellar material. At some point, the swept up mass becomes comparable to the ejecta mass. Then, the remnant's dynamics shift. A forward shock moves into the interstellar medium. A reverse shock can move back into the ejecta, heating it. Instabilities can form at interfaces. Clumps can survive and create filamentary structure. The remnant becomes a complex, layered system. X-ray observations can highlight shock-heated regions. Time-lapse can show expansion. Differences in expansion speed across the remnant can reveal differences in density and environment. So when Chandra shows a remnant changing over decades, it is showing the forward march of a shock through space. That is the hard science. And the soft feeling, if you want it, is this. Even an explosion becomes a slow drift when you zoom out far enough. Now, Cassiopeia A. Cas A is a treasure chest of element mapping. In a core collapse supernova, layers of the star contain different elements produced by different burning stages. In a perfectly layered, perfectly symmetric collapse and explosion, you might expect those layers to preserve some ordering. But real stars are not perfectly calm. Late-stage burning can involve convection and turbulence. The explosion itself can be asymmetric. Jets can form. Instabilities can mix material. So in Cas A, when we see silicon-rich material at larger radii than neon-rich material in some regions, that suggests mixing. It suggests that the star's interior had arguments before it died, flows and instabilities that moved material around. Again, we don't need to dramatize it. We can simply appreciate the evidence. It is rare in science to have a direct window into the interior dynamics of a star in its final days. Supernova remnants give us that window. The window is not perfect, it is indirect, but it is real. Now, we turn to one more calming module, how spectroscopy works in the simplest terms. Atoms have electrons. Electrons occupy energy levels. When an electron moves from a higher energy level to a lower one, it emits a photon with a specific energy. That energy corresponds to a specific wavelength, so each element has characteristic lines. In a nebula, collisions and radiation can excite electrons. Ionization can remove electrons. Recombination can bring them back. The balance of these processes depends on temperature, density, and radiation field. So by measuring emission lines, astronomers can infer temperature, density, chemical composition, and ionization state. In X-ray spectroscopy, lines can come from highly ionized atoms, iron, silicon, neon, and others, telling you about hot plasma and element distribution. In optical spectroscopy, lines like hydrogen alpha and oxygen lines tell you about photoionized gas. In infrared, molecular lines and dust features tell you about cooler components. Spectroscopy is, in a way, the quietest kind of detective work. You never touch the scene, you only collect the light, and from that light, you infer the conditions. Tonight, We are not doing the equations, we are doing the idea. The idea is enough. Now, as we approach the final third of our episode, I want to weave the three main exhibits together in a way that feels like closing a loop, because the cold, open promised loops and ledgers, we should honour that. In a planetary nebula, there is a ledger of photons. The central star emits UV photons. Those photons ionize gas. The gas recombines and emits light. Energy flows outward. The shell expands. Mass leaves the star. In a pre-planetary nebula, there is a ledger of dust and light. The star emits light. Dust scatters it. Geometry channels it. Arcs record episodic mass loss. Mass leaves the star. In a supernova remnant, there is a ledger of kinetic energy. The explosion imparts speed. Shock fronts convert speed into heat. Hot plasma emits X-rays. The remnant expands. Mass leaves the star violently. In all cases, the star's end is a redistribution of matter and energy. And in all cases, the nebula is the visible record of that redistribution. So here is the calm conclusion we can build toward. Nebulae are evidence, not ornaments. They are what you see when stellar evolution intersects with the physics of light. They are the places where a star's private interior products become public interstellar material. They are, in a quiet sense, the universe doing its housekeeping. Which brings us back to my office, because the office is a housekeeping system too. Dust gathers, air circulates, heat flows, light reveals. Papers are filed. The system stays within limits. It is defined as much by restraint as by action. A nebula stays within limits too. Photon budgets, pressure balances, shock physics. It is not chaos, it is complex order. Now, I'll offer you one last long, gentle drift, an extended closing that repeats the key ideas in a soothing way, without adding much new information, the way you might reread the last page of a file before you shut the folder for the night. A nebula is thin matter made visible by light. Sometimes the light is borrowed. Starlight scattered off dust in a pre-planetary nebula, like the Egg Nebula, where arcs and shells suggest episodic mass loss over centuries. Sometimes the light is earned. Ionized gas glowing in a planetary nebula, shaped by slow AGB winds, fast central star winds, compressed shells, and a changing ultraviolet lamp at the center. Sometimes the light is forced. Shock-heated plasma radiating in X-rays in a supernova remnant, where motion becomes heat, and heat becomes photons, and photons carry evidence across space. The shapes are not always what they first appear to be. Rings can be wastes seen pole on. Spheres can be bipolars in disguise. Brightness can be a matter of conditions, not a measure of mass. So we stay patient. We look in more than one wavelength. We use spectroscopy. We use time baselines. We let the nebula tell us what it is, rather than insisting it be what we first imagine. And over time, we get better at reading. The nebula is not a single scene. It is a record of flow, a record of shedding, a record of interaction, a record of energy moving from one form to another. In that way, it is like a ledger. And in that way, it is like this office, quiet, bounded, full of subtle currents, with a lamp that makes the invisible visible. I rest my palm on the folder. Nebulae, it says, a plural that hints at variety, a category that contains multiple endings and multiple kinds of light. Outside, the sky remains dark, uncomplicated, and vast. Inside, the desk lamp keeps its steady pool of warmth. I think of the Egg Nebula's faint, scattered beams. I think of the ring nebula's bright waist and hidden lobes. I think of Kepler's Remnant expanding, a shock front you can watch across decades. I think of Cassiopeia A's element maps, the star's interior motions written into debris. And I find, in all of it, a gentle reassurance. The universe is not hurried. Even when it explodes, it spends centuries cooling and expanding. Even when it sheds an envelope, it does so over thousands of years. Even when it shapes a nebula, the shaping is the cumulative result of small pushes applied over time. So if your mind is busy tonight, you can borrow that pace. You can let your thoughts expand slowly like a shell. You can let them cool like shocked plasma, settling into quieter radiation. You can let them scatter like light through dust, soft, indirect, harmless. In the end, the file closes the way it opened. Not with a bang, not with a parade. With steady work continuing, with a loop kept closed, with the ledger balanced. I slide the Nebulae folder back into its place. The desk lamp hums, the room stays warm, and the sky outside remains a dark slice of space, waiting patiently, full of thin clouds of evidence that we can read whenever we're ready. Tonight, we've read enough. Good night.